Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about solution for non-uniform torsion or Vlasov torsion. So before we go into that, let us look at the limitations of the previous solution for torsional constant, J. So we have a circular cross-section subjected to torsion here. You also have a non-circular cross-section subjected to torsion. So T is given as Gj theta, where T is the total external applied torsional moment and Gj theta represents the total internal resisting moment. The equilibrium is achieved primarily due to torsional rigidity Gj of the cross-section. However, in practice, the members in a steel structure are connected to adjacent members through various types of connections. Hence, the twist and warping deformation may be prevented at the ends of the member. Here, let us look at how warping is prevented in practice. Now, the typical pre-engineered steel building is shown on the right-hand side. Here we have two types of connections. Connection 1 is the ridge or apex joint. We can see the rafter on the left-hand side and the rafter on the right-hand side is getting connected through the end plate. Likewise, you have the connection 2, which is the eaves or knee joint. You can see the end of the rafter connected by an end plate to the top of the column. And both these connections prevent any types of axial deformation. Hence, warping is restrained. Now, let us look at how twisting is prevented in typical connections in pre-engineered steel building. So, you can see a column. The column has the exterior flange as well as the interior flange. The exterior flange is connected by a bracket, and on top of the bracket, the girt is sitting. And then on the interior flange, the fly bracing is connecting both edges of the flanges by connecting it to the girt, as you can see here. This type of connection is also known as fly bracing. Basically, the girt is resting on top of the bracket, which is giving restraint to the exterior flange, and the interior flange, the restraint is provided by the fly bracing, which is an angle section. This type of connection actually prevents any movement in the minor axis. Hence, the minor axis will undergo the second mode of buckling. In essence, what we are trying to say here is that there will not be any twisting acting at that cross section. Now, let us look at another connection here. This is basically the rafter. On top of the rafter, you have a purlin. The purlin is connected by a clip angle, also known as cleat angle. And then it is connected on the top flange by the cleat angle, and the bottom flange is connected by fly bracing, basically angle section similar to what we saw in the last picture. And this is a closer look of the typical rafter to purlin connection. And you can see here, this type of connection also prevents twisting of the cross section. So the total internal resisting moment is Gj theta plus something. So one is due to torsional restraint and another is due to warping restraint. Now let's look at the solution for members under torsion with a warping restraint, also known as non-uniform torsion. Let us consider a cantilever beam made up of an I section subjected to an end moment at the free end. The other end is fully fixed through a plate. Since the member is made up of a non-circular section, it develops both twisting and warping. However, the twisting and warping are prevented due to the fixed end of the cantilever beam. The equilibrium equation is given as total external torsional moment T is equal to the resistance offered by the restraining warping, which is T1, plus the resistance offered by restraining twisting, which is T2. T2 is, we already know that it is equal to Gj theta. So at the free end, we have the resistance completely by torsional shear, as you can see from the picture on the right hand side. This is also known as uniform torsion or self-enhanced torsion T2, which is taking place away from the support. In between the supports, the resistance is offered by lateral shear plus torsional shear. And at the support, there is non-uniform torsion T1 that is taking place, and it is resisted by means of warping normal stresses and lateral shear in the flanges. So now let's look at the torsional resistance offered by restraining warping T1. When the warping of the cross-section is prevented, a normal stress distribution that prevents warping occurs at the restrained end. In addition, a lateral shear V sub F is developed in the flanges at the restrained end to balance the applied torsion. Hence, the resistance offered by the restraining warping T1 is given as T1 equal to V sub F into H. Now, let's rewrite V sub F in terms of lateral displacement of the flange U sub F. So, from the relationship between shear force V and bending moment M, we have V equal to dm by dz. So, replacing V by V sub F and M by M sub F, we have V sub F equal to minus dmf by dz. The negative sign is basically when Z increases, M sub F decreases, as you can see from the picture below. So the origin of Z is taken from the left hand side of the beam where it is fixed to the plate. Now expressing lateral bending M sub F in each flange in terms of lateral displacement of the flange U sub F. So from moment curvature relationship for pure flexure, M equal to EI into d square V by dx square. So substituting I equal to I sub Fy by 2 and V equal to U sub F. So what is I sub Fy? Basically, it is the flange resistance divided by 2 in the minor axis. So M sub F is given as EIFy divided by 2 into d square U sub F divided by dz square, which is now equation 3. So here some assumptions are made. The assumption 1 is that the section is doubly symmetric with flanges of equal dimensions, as you can see from the picture on the right hand side. In the total moment of inertia of the flanges about y-axis is given as IFy, and the moment of inertia of top flange is IFy by 2 and the moment of inertia of the bottom flange is IFy by 2. Now substituting the value of M sub F into equation 2, we have V sub F equal to minus dmf by dz, which is nothing but minus d by dz into EIFy by 2 into d square U sub F by dz square. So now we have minus EIFy by 2 into d by dz of d square U sub F by dz square. So which gives rise to the equation Vf equal to minus EIFy by 2 into d cube U sub F divided by dz cube, which is equation 4. Now V sub F is given as minus EIFy by 2 into d cube U sub F divided by dz cube, which becomes equation 4. Now substituting the value of V sub F from equation 4 into equation 1, we have T1 equal to V sub F into H. So that is nothing but minus EIFy by 2 into d cube U sub F by dz cube into H, which now becomes equation 5. Now let us rewrite U sub F in terms of gamma. The relationship between twist of cross-section gamma and the lateral displacement in flanges U sub F is given by the picture shown below. So using trigonometry, we have tan gamma equal to opposite by adjacent, which is U sub F divided by H by 2. For small values of gamma, tan gamma equal to gamma. So gamma equal to U sub F divided by H by 2. So U sub F equal to H by 2 into gamma. Now differentiating that with respect to Z, we have du sub F divided by dz equal to H by 2 into d gamma by dz. When we twice differentiate it, we get H by 2 into d square gamma by dz square. And we differentiate it thrice, we have H by 2 into d cube gamma by dz cube. Now why do we do so? Because we can substitute this value in equation 5 above. So when we substitute the value of d cube u sub F by dz cube into equation 5, we have T1 equal to minus EIFy by 2 into H by 2 into d cube gamma by dz cube into H. So this becomes minus EIFy into H square by 4 into d cube gamma by dz cube. So this IFy into H square by 4 becomes the warping constant for an I section, which is also known as I sub W. So this T1 equal to minus EI sub W into d cube gamma by dz cube. So the equilibrium equation, total external torsional moment T is equal to the resistance offered by the restraining warping T1 and the resistance offered by restraining twisting, which is T2, and T2 is given as Gj theta. So substituting the value of T1 in equilibrium equation, we have T equal to T1 plus T2, which becomes T equal to minus EIW into d cube gamma by dz cube plus Gj theta. So T equal to minus EIW into d cube gamma by dz cube plus Gj into theta can also be represented as d gamma by dz. Now this becomes the generic equation for a member subjected to torsion. Points to remember. So the generic equation for a member subjected to torsion is given as T equal to minus EIW into d cube gamma by dz cube plus Gj into d gamma by dz. So let's look at Gj. The Gj is also known as torsional rigidity, which is nothing but the shear modulus into torsional constant J. Annexure E of page 129 of IS 800, 2007 gives you the J value for open cross sections, which is J equal to sigma n equal to 1 to up to infinity into Bi into Ti the whole cube by 3. And open sections are defined as I sections, channel sections and angle sections. And for closed cross sections, J is given as 4ae square divided by sigma b by t, also given in IS 800, annexure E, page 129. And hollow sections are basically defined as the sections that are on the right hand side. Basically, it is a closed cross section. Now, let's look at EIW. The EIW is nothing but modulus of elasticity into warping constant IW, also known as warping rigidity EIW. So for a doubly symmetric cross section, IW equal to IFY into h square by 4. For I section monosymmetric about minor axis, IW equal to 1 minus beta sub f into IY into h square, where beta sub f is equal to IFC divided by IFC plus IFT, where IFC is the moment of inertia of the compression flange and IFT is the moment of inertia of the tensile flange. This is given in Annexure E of IS 800. But now how do we relate monosymmetric cross sections to a doubly symmetric cross sections? So we need to find out the value of beta sub f. For doubly symmetric cross sections, IFC equal to IFT, which means that beta equal to IFC by 2 IFC, which will indicate beta sub f equal to 1 by 2. Right? So when we substitute 1 by 2 in the above equation, we have 1 minus 1 by 2 into 1 by 2 into IY into h square. So which gives rise to the value IW equal to IFY into h square by 4. Now the annexure E also tells us that for cross sections such as hollow, rectangular, square, T and angle, the value of I sub W is equal to 0. As you can see from the right hand side where it is marked in yellow color. What about channel sections? What is the value of I sub W? Now let's talk about the generic equation for warping constant I sub W. Consider a member with an arbitrarily chosen shape defined in XYZ Cartesian coordinate system with thin-walled cross-section as shown in the figure above. Let the cross-section be defined by polar coordinate axis and S coincides with the center line of the cross-section and has its origin at the boundary point 1 and ends at the boundary point N with coordinate S equal to B. Assume Px, Py, Md be externally applied loads and N, Qx, Qy, Mx, My and T omega be the internal forces. Let's consider a small rectangular wall element of dimensions ds and dz. A blown up view is shown on the figure on the right side with thickness T. The figure also shows the forces that are acting in the z direction. Note, in the thin-walled cross-section, the through thickness deformation is usually negligible. Hence, the axial stresses and the shear stresses along the center line of the walls are assumed to be representative of the stress. Now, let us look at the equilibrium for the wall element shown above. So, we have sigma z plus dou sigma z by dou z into dz into t into ds minus sigma z t into ds plus q plus dou q by dou s into ds into dz minus q into dz is equal to 0. So when we expand it, we get 4 terms gets cancelled. The first term as well as the third term is getting cancelled, as well as the fourth term and the last term is also getting cancelled. Now we have dou sigma z by dou z into t plus dou q by dou s into ds into dz equal to 0. However, ds multiplied by dz is not equal to 0. Hence, dou q by dou s plus t into dou sigma z by dou z is equal to 0. So, this becomes equation 1. Here, q is the warping shear flow, which is produced due to deformation along S, that is V direction, and sigma z is the warping normal stress produced due to deformation along Z, that is W. Note, the through thickness deformation U is negligible in the thin-walled cross sections. So, now we have to derive expression for q as well as sigma z. Now, we also know that the deformations in the wall element U is very close to 0 and V and W not equal to 0. So, before we proceed to find out the equation for Q, let's derive the expression for sigma Z. So, compatibility condition of deformation in wall element. From compatibility condition, we know that the shear strain due to V, that is the transverse deformation, and the axial deformation W, that is displacement components in Cartesian coordinates x, y and z, is given as gamma yz equal to gamma zy equal to dou w by dou y plus dou v by dou z. And this can be represented in the polar coordinates as gamma equal to dou w by dou s plus dou v by dou z. Now, rewriting tangential displacement v in terms of zeta, eta and phi, we have dv equal to d zeta cos alpha plus d eta sin alpha plus h sub p into d phi. Here, h sub p is the perpendicular distance from the shear center to the tangent to the center line of the cross section. Now, for a point A, we have a tangent line at point A and then we have the shear center S. This perpendicular distance is represented as h sub p. So now we have dou v by dou z equal to dou zeta by dou z into cos alpha plus dou eta by dou z into sin alpha plus h sub p into dou phi by dou z, which becomes equation 2. Now considering the twist deformation phi due to torsion, we can say that the first two terms will be 0. So hence, since we are looking at only the twist deformations, dou v by dou z equal to hp into dou phi by dou z, which is equation 3. From strain displacement relation, the shear strain gamma is given as dou w by dou s plus dou v by dou z, which again will be equal to 0. Since we are ignoring the longitudinal shear strain gamma due to warping, our focus in this current study is only for the warping normal stresses. So dou w by dou s equal to minus dou v by dou z, which is equation 4. Now substituting 3 in equation 4, we have dou w by dou s equal to minus dou v by dou z, which implies dou w by dou s equal to minus hp into dou phi by dou z, which becomes equation 5. Integrating equation 5 on both sides with respect to s, we have integral of dou w by dou s into ds is equal to minus hp into integral of dou phi by dou z into ds plus w naught of z. Here w naught of z is basically a constant since it is integrated on both sides with respect to s. So w is equal to minus phi dash into integral of hp into ds plus w naught of z, which is equation 6. Now from Hooke's law, we have sigma z equal to Young's modulus into epsilon z. So that is equal to E into dou w by dou z, which becomes equation 7. Now we can differentiate equation 6 with respect to z. We have dou w by dou z equal to minus phi double dash into integral of hp into ds plus dou w naught of z by dou z. So substituting dou w by dou z in equation 7, we get sigma z equal to E into dou w by dou z, which is equal to E into minus phi double dash integral of hp into ds plus dou w naught of z by dou z, which becomes equation 8. Finding the value of dou w naught of z by dou z. So using equilibrium conditions, we have integral of sigma z into dA equal to 0, which is the summation of the forces in the z direction is equal to 0. Now substituting sigma z, we have E into minus phi double dash into integral of hp into ds plus dou w naught of z by dou z into dA is equal to 0. So minus E phi double dash into integral of hp into ds into dA plus E into integral of dou w naught of z by dou z into dA is equal to 0. So when we take the second term to the right hand side, we can cancel minus E on both sides. So we have phi double dash into integral of hp into ds into dA is equal to dou w naught of z by dou z into dA is equal to dou w naught of z by dou z into A. So this gives dou w naught of z by dou z equal to phi double dash into integral of hp into ds into dA by A. Now we can substitute this value of dou w naught of z by dou z in equation 8. So we have sigma z equal to E into minus phi double dash into integral of hp into ds plus phi double dash into integral of hp into ds into dA divided by A. So we can take minus phi double dash outside and we get this equation as you can see above. And here this integral of hp into ds minus integral of hp into ds into dA by A is called as the normalized sectoral coordinate omega. So sigma z becomes minus phi double dash into E into omega. Now substituting the value of sigma z in equation 1 to obtain Q. So equation 1 is given as dou q by dou z. So equation 1 is given as dou q by dou s plus t into dou sigma z by dou z equal to 0. So this means that dou q by dou s plus t into dou by dou z of sigma z is given here as minus phi double dash E into omega is equal to 0. So integrating on both sides with respect to s, we have integral of dou q by dou s into ds is equal to integral of dou by dou z of phi double dash into E into omega t into ds plus q1 into z, which is the constant. Now this q1 of z is equal to 0 because it represents the shear flow at the beginning of the region of the integration, which was taken at a free boundary. So the elemental shear flow q is equal to phi triple dash E into integral of omega t into ds. Now let's look at the cross section here. At point A, we have a shear force Q into ds, and tangent to the point A is given by this dotted line. The shear center is given by S in green color, and the distance between the tangent at point A and the shear center is given as plus HP. The resistance to applied torsional moment T is obtained by summation of the moments of the elemental shear forces Q into ds acting along the middle line of the section about the shear center. Now this T omega is given as Q into ds into HP. So Q into ds is the force and HP is the perpendicular distance which leads to the moment. So here again, where HP is the perpendicular distance from the shear center to the tangent to the center line of the cross section. Now here in the sign convention, we need to take into account it is positive when the vector from the shear center to the point considered on the cross section sweeps in the counterclockwise direction along the increase of S. Now to understand this more carefully, let's look at another point B, which is given here. So if you take this point, the tangent to the point is given in the dotted lines again. So the distance between this one is taken as negative HP because this will be acting in the clockwise direction about point S, which is the shear center, and hence it is given as negative HP. Now S is the distance along the center line of the cross section, and this T omega is equal to integral of Q into ds into HP is given as integral of phi triple dash E into integral of Wt into ds into HP into ds. Basically, we are substituting the value of Q, which is the elemental shear flow, given as phi triple dash E into integral of omega t into ds. We know that omega equal to integral of HP ds minus integral of HP ds into dA divided by A, which is equal to omega s minus omega s bar. Let's assume that way. So here, omega s, which is equal to integral of HP into ds, is defined as the warping function or sectorial coordinate. And integral of HP into ds into dA divided by A is equal to omega s bar, which is the average value of omega s. Since omega s bar is average value of omega s, it is independent of s, we can rewrite warping function omega s as HP into ds equal to omega s, which is equal to HP into ds equal to d omega s by ds minus d omega s bar by ds. We are doing so simply because this omega s bar is a constant, so differentiation of constant is 0, so it doesn't make any difference. So we are adding to this equation, and this again can be simplified as d by ds of omega s minus omega s bar into ds. So in this equation, we are multiplying with integral of omega s minus omega t into ds and integrating with respect to s on both sides. So when we do so, we get this equation as shown in the screen here. So let us look at solving the right hand side of the equation, which is integral of omega s minus omega s bar into t into ds into dw into d by ds of omega s minus omega s bar into ds. Basically, we are substituting HP into ds as d by ds of omega s minus omega s bar into ds. So this is clearly shown in the red color fonts. This gives rise to the equation du equal to t into d by ds of omega s minus omega s bar and v equal to omega s minus omega s bar. So applying the UV rule, we have du equal to t into d by ds of omega s minus omega s bar and v equal to omega s minus omega s bar. When we substitute that, we get the following equation here. This can be simplified as integral of omega s minus omega s bar the whole square into t into ds minus integral of omega s minus omega s bar into t into ds into d by ds of omega s minus omega s bar. Now assume the normal stresses of intensity P are distributed uniformly over the end cross section of the bar. This P is basically representing the warping normal stress. These stresses produce no rotation of the bar. Basically, they only produce axial displacement, which is nothing but warping, and as a result, there will be no work done with torque TW because here there is no twisting that is happening in the cross section. From reciprocal theorem, we can conclude that the work done by the stresses P on the warping displacements omega produced by torque T sub W or T omega must vanish. Thus, we have integral of P into T into ds into omega is equal to 0. So P into T into ds into omega s minus omega s bar is equal to 0. So when we take this P outside, P into omega s minus omega s bar into T into ds is equal to 0. Here P cannot be 0. So integral of omega s minus omega s bar into T into ds is equal to 0. Now let's substitute that in this equation. Therefore, the second term on the right hand side becomes 0. So now we have this integral as RHS becomes integral of omega s minus omega s bar the whole square into T into ds. So the right hand side of the equation is nothing but integral of omega s minus omega s bar the whole square into T into ds. So substituting the value in the above equation, we have T omega equal to integral of P triple dash into E into integral of omega T into ds into HP into ds. Now this P triple dash is nothing but d cube omega by dz cube, which is not a function of s, so it can be taken outside the integral. So which gives rise to the value P triple dash into E into integral of bracket open integral of omega sub s minus omega sub s bar into T into ds into HP into ds. So here we have substituted instead of omega, we have substituted omega equal to omega s minus omega s bar. But now this entire term that is shown in the bracket actually is derived previously. So we can substitute that as you can see from the red color boxes. So we have this equation boiled down to P triple dash into E into integral of omega s minus omega s bar the whole square into T into ds. So now warping torsion becomes T omega equal to P triple dash into E into integral of omega s minus omega s bar the whole square into T into ds. Now let's look at what is the bending moment equation. So the bending moment equation is mx equal to EI into V double dash, which is equal to V double dash into E into integral of x square into dA is the moment of inertia Ix, and then V double dash is equal to the bending curvature d square V by dz square. So similarly, the integral of omega s minus omega s bar the whole square into T into ds can be termed as warping constant I sub W. So the units of this warping constant omega s minus omega s bar the whole square into T into ds is equal to millimeter square minus millimeter square the whole square into millimeter. So we get millimeter power 6. So unlike moment of inertia, the warping moment of inertia basically is millimeter power 6, whereas regular moment of inertia is millimeter power 4. So the point to remember, the cross sections with IW equal to 0 are angle T and cruciform cross sections, because the shear center coincides with the point of intersection of the component plates, which means that the head sub P is equal to 0, which indicates that omega s minus omega s bar is equal to 0. Now for solid circular cross sections and circular tubular cross sections, there is no warping. For narrow rectangular cross section as well as box cross sections, the warping is negligible. With this one, we will complete the portion on torsion. We will come back to the beams in the next class. Thank you very much.